Thank you for the introduction. So today's talk is about wind farm flow effects and specifically so-called wind farm blockage effects. This is about an experimental work that we did here in the lab, and it's mainly the work of two master students, which are Camilla Aasnæs and Joachim Bjørnsen, who worked on this during the last 1.5 years. So Joachim is here with us today and probably can also answer questions if they're very specific in the Q&A session. Camilla, who was supposed to give this talk, got a new job and is offshore right now. So, so she is excused. Okay, so today's talk is about wind farm blockage or wind farm flow effects. And this was a big topic in the media in the end of 2019, where first Wind Power Monthly came out with that the Danish offshore giant Ørsted was overestimating the power output of its offshore wind farm, and that they were downgrading their long-term targets and also reducing their internal rate of return by 0.5%. Then some other news picked up on that. Here in Norway, it was Dagens Næringsliv who picked up on that 2 weeks later and reported about this blockage effect in wind farms that wasn't so well known before that, and also said that the stocks of, or like the stock market reacted on this, and Ørsted stocks went down by 8% after this announcement. So what is that, what everyone is talking about? So we see here a picture, a very famous picture of the offshore wind farm Hornsrev. And in this picture, it is unique that we actually can see the so-called wake effects. Wake effects, most of you might have heard of them by now. These are downstream region behind a wind turbine rotor where it's lower kinetic energy. And if that downstream region hits a downstream wind turbine, that can extract less energy, of course. But in addition to that, and what we cannot see in this picture is that there is always a small region upstream of a rotor where the velocity is reduced. And this small region is sometimes referred to as an induction zone. So this is a smaller region upstream of a wind turbine, and whenever a flow is approaching an object, it has to slow down. So this is also something that is well known, but what was new at that time is that there is individual induction zones, or so-called blockage effects of individual wind turbines, also next to this turbine here, and there could be also induction zones of these downstream wind turbines. And what Ørsted said is that these individual blockage effects for every turbine, that they add up to a global effect, which might be larger than the sum of those individual effects. And yeah, shortly after this press release, also the industry consultant DNV came out and said that these blockage effects led to underestimation of the power output, and these are in a region between 0 and 4% of the mean annual energy yield, so quite significant here. So what do we do about it? That we want to investigate this in a very basic manner in the lab scale, and we want to see if we can see those blockage effects in small wind farm arrangements. So we want to find out what the turbine separation, like the lateral separation of turbines, has to say on that effect. How many turbine numbers and rows could affect this, and also what the layout, if we have aligned layout of turbines, or if it's an offset or staggered arrangement of turbines, if that would influence the induction zone and also later on the forces and power of a wind farm. So these experimental data that we recorded, we want to use them as input also for validation of computational models. So these could be simple flow superposition models, which my colleague David Lande-Sundal is working on. And also we want to use them to create a digital twin in computational fluid dynamics. And this is where my colleague Gloria Steenfeld is putting a lot of effort in right now. Yes, so our experimental setup is that we tested this in our marine lab. This is a towing tank which has a length of 50 meters, a width of 3 meters and a depth of 2.2 meters, which is here in the basement of HVL in Bergen. And we set on one of the towing carriage setup of a submerged wind farm, which could look like this. So this is the biggest arrangement that we investigated. We see 7 rotors, and they are turned upside down and submerged underwater. So this is let's say an underwater wind farm. Could be more actually of in reality correspond to a tidal farm of tidal energies, but we can say that this is scalable also to wind farm effects. Then upstream of then these single wind turbine rotors, we don't actually use rotors. We are looking at a larger scale, so we're using porous discs with a thrust coefficient of about 0.9 to represent the induction of a wind turbine rotor. Of course, this is not completely accurate. This is just a simplified model of a rotor, but as we see for farm scale, as we look at farm scale effects, we hope that this is sufficient to create those induction zones as we want to see them. For the actual flow measurements, we use a device called Victrino Plus ADV, which is an acoustic Doppler velocimeter and measures actually particle movements in a small volume. And we can adjust that upstream of this wind farm and measure flow velocities, in this case upstream. So the whole setup is towed towards left, and the relative inflow to the wind farm is from the right then. So this is what it looks like in the lab. So this is the 2 towing carriages. The first one has this measurement device underwater. So these little sticks that go underwater carry the discs. This is an underwater picture of this wind farm where we're just adjusting and aligning those discs. So we have some here in this first row and some in the second row. And here I should actually have a little video of the discs being moved relative towards the water. And here we're actually doing a wake measurement instead of a blockage measurement downstream of this one disc. Okay, so our measurement layout was a little bit different. Basically, we measured both in the wake, so a couple of distances in the wake behind the wind farm, but today I'm actually just talking about this so-called upstream induction zone, which we focus on. So we measured basically 6 different setups that I'm going to present today. The first 3 setup is just a 1-road wind farm consisting of 3 discs next to each other. So we call this wind farm 3, and we have them in different separation distances. So this was basically Joachim's master project, where he changed the distance from 3 discs that were really tied into each other to a spacing where we have 1 rotor diameter between the discs, and then even a larger separation distance of 4 diameters, which is more realistic than to real wind farms. Then Camilla's master thesis was basically to build up on that and add a second row of turbines and investigate the influence of a second row. So first of all, she just looked what 2 turbines that are in an offset arrangement can do. Then she added 3 turbines in a line setup, and also finally 4 downstream disks in, again, a offset setup. So the results of this first setup that we tried, so this is just 3 aligned disks in 1 row, and we measured the upstream velocity in a distance of 1 rotor diameter upstream. So these are the red points, and even closer to the disks, which are the blue points, which gave then, of course, a higher velocity reduction. What we can see here in those graphs is that we have those 3 disks really tied into each other, that the upstream induction zone is actually merging. So at 1D upstream, we get an almost Gaussian distribution of the velocity deficit, whereas at 0.4, we see small variations. And this is because there is, in the 3rd dimension, there is some space in between the disks. But we see it clearly that those induction zones are merging into one induction zone, and that the velocity reduction in front of the central disk is significantly larger than on the neighboring disks. If we increase the separation distance now, we see that the induction zones get separated more and more, but still that there is some interaction in between. So they are not completely separated from each other. For the highest separation distance, or here it should be a 2 and a 4, we see that these profiles here, those upstream velocity profiles, are more or less independent, that they have a very similar shape, both at 0.4D and at 1D upstream, and that they're a Gaussian, and in between the disks, we actually get a little bit of a speed up effect, and those zones don't really merge. Let's now look at a full flow field of these 2-road wind farms that we investigated, which we call then Wind Farm 5, Wind Farm 6, and Wind Farm 7. Wind Farm 5 and 7 are offset setups. Wind Farm 6 are aligned setups. And this is a interpolation of all the measurements that we did on these black circles here. They are not completely accurate, but it shall give you a picture of how the flow within those wind farms could approximately look like. I've whitened out some regions where some interpolation errors occurred. So what we're looking at today in this talk is the upstream region. Again, 0.4 and 1D upstream of the 2 front row disks here. So this is the region that we're focusing on. And what we wonder about is this region upstream being influenced by the arrangement downstream. So here are the results. And what we basically can see, also compared to the 3 turbines of the first row, is that for the Wind Farm 5 and the Wind Farm 7 setup, we get very similar upstream regions. We do not really see that there is a blockage effect from the downstream turbines that is influencing the region just in front of this central disk and also this disk. It's slightly influencing the region in between the disks. So where we previously had a speed up effect between the disks, it's now being influenced by a downstream disk, which is actually 14 downstream in this case. And of course, we see a small influence of this outer disk here. But the most significant change of the upstream induction region is actually at this wind farm 6 setup, where we get higher velocity reductions upstream of both the central and also this outer disk here. So while the velocity reduction here at 0.4 was only about, let's say 22%, it's going to about 27% in these cases. So we can assume that a aligned setup is having a higher influence on those individual zones. If we compare now the induction zone at x over d -1, which is 1 diameter upstream for different cases, we see that actually for a single rotor or for a single turbine or single disk, it's very similar to this wind farm 3 setup with a large separation distance. Also, the wind farm 5 and the wind farm 7 setup have a very similar upstream induction zone measured at this 1 diameter upstream. And the only case that is a little different here is actually this wind farm 6 case, where we had aligned turbines, and we see a higher reduction of this zone upstream the front row. Okay, so let's come to some conclusions. What we did see with those experiments, that for one row that we get significantly larger inductions at the central turbine for a decreasing separation distance. And if we have them very tightly spaced, these induction zones are clearly merging into each other. And for larger separation distance in our investigation, they were larger than 4 rotor diameters, we did not really see that they were significantly influenced. Also, the measurements were quite independent of the neighboring disks in this case. For this 2-row wind farm, we tested an offset or 2 offset setups and an aligned setup. And for the offset setup, we didn't see any significant influence on the upstream induction zone either. But for the aligned setup, we saw a small increase in this induction on the central upstream turbine, or basically also all the upstream turbines. So these are just like a couple of results, and of course we cannot conclude from that how large those effects are actually in real wind farms, and we did not solve all of the research goals that we have. So there's a lot to do again. So one thing that we will do is that we're doing more detailed measurements in this induction zone using a PIV instrument, which is giving us a complete flow field. We will use a larger number of disks, both in the front row and also especially extending downwards. How is more turbine rows influencing the whole situation? We want to complete this with thrust measurements on the individual disks, and maybe at some point also replace the disk by rotating devices with a power outtake. And another thing that we think is influencing this quite a lot is the turbine height, which is in our experiments the turbine depth in relation to its own rotor diameter, which is influencing the so-called local blockage. And another thing is also like the local boundary layer height in a real situation, and in our situation would be the depth of the flow channel. And also, as I already mentioned, we want to use this for developing flow superposition models and also create a digital twin in CFD, which is supporting those measurements. Yeah, that was my talk for today. Thank you for your attention. This is actually Joachim and also Camilla working in the lab and setting up their experiments with 3 disks and up to 7 disks. Thank you.